Bismillahirrahmanirrahim. We will continue from where we have left. First of all, in this picture, that is figure 1.4.3. This figure actually shows the relationship between the input signal frequency f plotted along x-axis, and along y-axis you are having your reconstructed frequency. That is the frequency of the reconstructed signal. What we observe here, that your along x-axis where you are having your signal frequency f, it is the scale is being marked after every sampling frequency fs. Okay, then fs, then 2fs and 3fs, so on. And also your Nyquist interval, that is between minus fs by 2 till fs by 2, is also marked over this x-axis. What is we observe from here, if your input signal f is between 0 and fs by 2, it means whatever is your signal frequency, it would be reconstructed as it is. It means the signal frequency would not be aliased, and the reconstructed signal would have the same signal frequency as your applied input frequency f. Okay, so it means the signal f that is being sampled is having the same frequency after being reconstructed, and it happens when your signal frequency is between Nyquist interval till Nyquist interval, within Nyquist interval, that is from 0 to fs by 2. Next, what we observe, that if your signal frequency increases from fs by 2 till fs, that is the second half here, that here it is fs by 2 and here it is fs. In this range of your signal frequency, what happens, that your reconstructed frequency fa, that is plotted along y-axis, is now being appeared as a negative frequency. Okay, so this is appearing as a negative frequency, and this you can verify. For example, just take your fs as 10 hertz. Okay, just do this calculation yourself. We have already done within the class. That is this fs, take this fs as 10 kilohertz. You can just take it as 10 hertz. Doesn't matter it is kilohertz or hertz, just take it as 10 hertz. And then consider three cases of f. That is, first take f that is equals to 4 hertz. Means for 10 hertz sampling frequency, your Nyquist interval would be plus minus 5 hertz. And if you are taking your signal frequency f4 hertz, it means it will lie somewhere here. So it means you are having your 4 hertz, and when you will generate your set of replicated frequencies from f plus minus mfs relation, you will see that only the signal frequency that will be reconstructed. The reconstructed frequency would be the one that is reconstructed through your low pass filter, that is connected as a post filter after sampling. And we, as we have already discussed, that the cutoff frequency for the post filter is also set as fs by 2. Therefore, the reconstructed signal, that is of 4 hertz, because your input signal is 4 hertz, and for this 4 hertz, if you are using a sampling frequency of 10 hertz, it would be sufficient for it. It meets the Nyquist criteria. It means the reconstructed signal would also be 4 hertz. In this way, there would be no aliasing. Whatever the signal applied, the same has been reconstructed. Okay, so this would be the case when you will take f as 4 hertz. Then take f as plus 5 hertz. Then if you just take as f as fs by 2 equals to fs by 2, you will see that from the replicated set of frequencies, you will have plus minus fs by 2 frequencies available to you. Means you have applied 5 hertz frequency, but you will get how much? What? You will get plus minus 5 hertz at the output. It means you will get two frequencies, and it is being verified from here, because when your x-axis frequency is fs by 2, you are having plus fs by 2 here and minus fs by 2 here. It means the aliased frequency components would not be the just signal a single 5 hertz frequency, but it would be plus minus 5 hertz. Later, apply f is equals to 6 hertz. When you will apply f is equals to 6 hertz, it means now your signal frequency is beyond fs by 2. It will lie somewhere here. So it means in this case, what you will observe that you will have negative frequency only. For example, if you are applying 6 hertz, just check and get the calculations. You will get minus 4 hertz are available to you. It means it will lie here. This way you can verify this curve, and the conclusion for this curve is what? Whenever your signal frequency is lying within the Nyquist interval plus minus f is by 2, it means the Nyquist criteria has been fulfilled, and only then your analyzed or reconstructed frequency would be the same as f. But the cases when your f is beyond this plus minus f is by 2 region, in that case the reconstructed signal would be analyzed one. It would not be same as f. This is for this figure. Later, we will do some problems over it. This we have done, example 1.4.1. In this case, we have done. Now I will just discuss another problem here. In this case, you will see here. For example, I will go back. For example, your sinusoidal frequency f is of 10 hertz. And what is the case here? You are having the sampling frequency of 12 hertz. It means your sampling frequency is not sufficient for this 10 hertz f. And the replicated frequency would be f plus minus mfs, would consist of this set of frequencies. And how this set of frequencies generated? This 10 has been generated in the case when your m is 0. F is 10 hertz plus 0 multiplied by 12 hertz will give you 10 hertz back. Then this 22 is obtained through F plus MFS, but here you are taking the value of M as 1. Then here and for this 34, you are taking the value of M as 2. And on my right hand side, you are getting your M as minus 1, then minus 2 and minus 3 and so on. It means what you observe from here, it means the effect of sampling in frequency domain is the generation of infinite number of set of frequencies, and this set of frequencies are generated due to sampling effect in time domain. In time domain, you get your sampled signal, but in frequency domain, extra high frequency spurious signals are included within your required frequency. And this is why. Can I ask you the reason for this is that when a continuous signal is just changed into a sampled signal, the sampled signal is having so much discontinuities that is, it is just having the signal at the sampling interval and then it goes to zero. It means you are having infinite rate of change of signal at points of sampling interval. And when you are having infinite rate of change of signal, it means the high free actually the high infinite rate of change signal can be corresponded as a high frequency component, and it means these such high frequency components would be added due to this discontinuities in the sampled signal. Whenever your signal is continuous, it means it would only consist the frequency that it is having, but once it is sampled out, extra frequencies are generated. Why these extra frequencies are generated? These extra frequencies are generated due to the effect of sampling and due to the effect of discrete time signal, which has so much discontinuities. It means, for example, at time instant of t, that is first sampling interval, it is having some signal value. Then till the next sampling interval, it has no value. Then again, it has a abrupt change of signal value at 2ts and minus 2ts, 3ts, minus 3ts, and so on. It means after every sampling interval, the spurious frequency components have been added. Okay. Now, what we have discussed in this picture, now we will see that after sampling of 10 hertz signal, when this 10 hertz signal is being sampled out at 12 hertz, you will generate so much frequency, so many infinite number of frequencies have been generated. But the question arises that what would be the signal frequency of the reconstructed signal? This may be showed that only the reconstructed signal will have the frequency that will lie between this Nyquist interval of minus 6 6. Why this is minus 6 and 6? Because for a sampling rate of 12 hertz, when you just divide this 12, it would be minus 6 and 6. So it means within this Nyquist interval, you will only get your this reconstructed signal back. It means if I compare this set of frequency, what you observe that within this minus 6 and 6 hertz interval, only the frequency component of minus 2 is lying within it. It means you have applied 10 hertz signal for sampling, but it would be reconstructed as a signal of minus 2 hertz. Okay, so this means your frequency has been aliased, it has been mixed up, you would not be able to get it back because the original signal frequency is 10 hertz. And why it has happened? It has happened because your sampling rate for 10 hertz should be minimum of 20 hertz, but you are undersampling this signal of 10 hertz. That's why you, in this case of 10 hertz, what you observe that you are having a light frequency component of minus 2 instead of this 10 hertz. The original signal was 10 hertz, but it would be reconstructed as minus 2 hertz, and this minus 2 hertz would be the signal that is lying between minus 6 and 6. Now the question arises that what is the effect of this negative frequency? Because mostly we are aware that the frequency is always positive, but here what would be the effect of this negative frequency? The effect of this negative frequency can be judged in the subsequent problems. For example, if you are applying a sine wave of 10 hertz, then it means the sine wave of 10 hertz would become as a sine wave of minus 2 hertz. So this minus 2 would appear in the argument of sine, that is sine of 2 pi minus 2. That means sine of minus 4 pi hertz. Then we know that sine of minus theta is what? It would be minus sine theta. It means this minus sign would come outside, and this minus sign then when coming outside would indicate a negative signal of this sine 4 hertz. It means this negative signal means what? Inverted signal. It means 180 degrees phase shifted signal. It means when you are having a negative argument in a sinusoidal function of sine function, then this negative frequency would produce an effect of inverted signal, that is 180 degrees phase shifted. But however, if you are using a cos signal as your input signal, cosine signal, in that case, cos of minus theta would be theta. So cos theta. It means there would be no effect of this negative frequency, and the cosine wave would not be altered. It would not be inverted. It would appear as it is. There would be no phase shift with if you are having a cos signal. Okay. Now we see that how this effect of aliasing can be avoided. This effect of aliasing can be avoided by setting your sampling frequency according to your input signal. Because now signal is 10 hertz, for its to be properly sampled, at least the sampling frequency should be 20 hertz. Then on the safe side, it has been taken as 22 hertz. For this 22 hertz signal, what you observe that now with this 22 hertz, your sampling, your Nyquist interval would be minus fs by 2. Sorry, plus minus fs by 2. This 22 hertz would be changed into a Nyquist interval of minus 11 and 11 hertz. It means this minus 11 and 11 would be your Nyquist interval, and whatever the signal frequency would be there, it would lie within this region. If you just observe and then again generate a new set of replicated frequencies, don't consider this one because this is for fs 12 hertz. Now generate another set of frequencies for taking f as instead of 12 hertz, taking it as 22 hertz, and then you will observe that your 10 hertz signal would lie within this Nyquist interval of minus 11 and 11 hertz, and the signal would be properly reconstructed. Okay, so this is your the basic concept applies here, that what would be the effect if you undersample your signal. Okay. Then again, in this example 1.4.2, now you are having a music signal, and for music it would be an audio signal. That's why its sampling rate would be 40 kilohertz. Okay, this we have seen. For this 40 kilohertz signal, your Nyquist interval would be half of it, that is plus minus it is by 2, that is from minus 20 to 20 hertz. Then you can have an effect. This minus 20 and 22 20 hertz would be the Nyquist interval, and whatever signal you will have, that frequency would be an audible one. If for example your inaudible frequency range, that is from fs greater than equals to 20 and less than equals to 60 hertz, will be aliased, because that does not come into an audible range. An inaudible frequency of minus 20 to 460 hertz would appear as 20 kilohertz. It means it would come into an audible range, and then it would be you can listen that frequency then. Okay, it means the sampling rate is very important, and until unless it is not properly defined, you would not be able to get your signal back. Okay, then again, on this next example we will switch. Now you are having five signals with you. These five signals are given here as this complete range: 14 pi t, then minus sine 6 pi t, sine 2 pi t, 10 pi t, 18 pi t, and so on. And they are all being sampled at 4 hertz. Okay, it means before identifying that either aliasing would be there or not, the first thing would be what? First thing would be this thing, that you have to identify the frequency is present, the value of frequency present in this signal. Okay, so it means you are having sine 14 pi t. So with this 14 pi t, what you think? This 14 pi t is representing what? This 14 pi t is representing your 2 pi ft signal. It means 2 pi ft means pi is there, 2 is there. It means the respective frequency would be 7. And if you are having this minus sign outside, it means you can see that it would appear as minus 7 hertz, as I have discussed. Okay, then comes this one thing, minus sine 6 pi t. It means this minus sign is again due to the fact that inside your frequency would be a negative frequency. Then sine of minus theta would be minus sine theta. So that's why here 2 pi f. It means f is here 3, not 3, just it would be minus 3. Then this minus 3 means then it is the minus sign is written outside. It means the next frequency for this signal would be minus 3 hertz. Okay, here. And likewise, the other frequencies would be 1, 5, and 9 hertz. You can check here. Here, for example, the last one would be 9. 2, 18 divided by 2 would be 9. Here, 10 divided by 2 would be 5. And then it would be 2 divided by 2 would be 1. So here, the set of 5 frequencies are there. And you are sampling all of them at 4 hertz. Okay. So if you just have a look over it, what you observe, that minus 7, minus 3, 1, 5, and 9, and you are sampling at fs is equals to 4 hertz. It means the replicated set of frequency would be this one, f. It would be the replicated frequency would be generated one after another for this complete set by f plus minus mfs. Okay, this you can do, and then you will get it. This 4 hertz frequency is only sufficient for this 1 hertz signal, and this my for 4 hertz frequency the Nyquist interval would be plus minus 2 hertz, plus minus 2 hertz, plus minus 2 hertz. So for this plus minus 2 hertz only, this 1 hertz frequency is lying within this range. The others are outside. Okay. So this you can see here, and it would lead to this aliasing effect. Again, the next problem is this: let x of t be the sum of sinusoidal signals. Here you are having how many frequencies here? Here you are having one frequency 4, then plus 3 cos pi t plus 2 cos 2 pi t plus cos 3 pi 4 plus cos 3 pi t, and so on. Then again, here the thing is that t is being mentioned in milliseconds. If t is being mentioned in t seconds, it means your frequency would be kilohertz. Okay, so here you will see that what would be the reconstructed signal. In this case, first we have to identify that what are the frequencies that are being sampled out, because here you are having a complex signal, and this complex signal is having all these four frequencies in it. It means for the first term it would be 0, and for the second term it would be, here it would be 2 pi ft, but 2 is not written here. It means f would be zero point 0.5, but st is in milliseconds, then f2 would be in 4 kilohertz. Okay, then f2 would be zero point 0.5 kilohertz. And similarly, for here 2 pi t, it means f is here 1, but not 1 hertz. It would be 1 kilohertz because t is mentioned in milliseconds. And then for f4 it would be 1.5 kilohertz. And here the maximum frequency is 1.5 kilohertz, that is your f4. So the Nyquist rate would be 2f maximum. It means it would be 3 kilohertz. Okay. If x of t is being sampled at 3 kilohertz, it means the sampling, they would be normalizing. But here we are observing that x of t is sampled at half of this rate. At half of this rate means what? It would be how much? It would be 1.5 kilohertz. And if it means the required sampling rate is 0 kilohertz and you are undersampling it at 1.5 kilohertz, then the respective Nyquist interval would be plus minus fs by 2. That is, for 1.5 kilohertz, it would be minus 0.75 and plus 0.75. Okay. What you observe from here, it means if you are undersampling at 1.5 kilohertz, only the first two signals, that is f1 and f2, will not be analyzed. Okay, it means here what is written, f1a would be f1. It means whatever the signal frequency f, it would be also reconstructed as same. It means 0 would be reconstructed as 0. And same is the case for f2 is equals to f2. Why? Because f2 is 0.5 kilohertz, and for this 0.5 kilohertz, the sampling of 1.5 kilohertz is sufficient. Okay, so it means here the reconstructed frequency component f2a would be same as f2. But however, for f3 and f4, they are lying outside the Nyquist interval. Why they are lying outside the Nyquist interval? Because you are having minus 0.75 and 0.75 the Nyquist interval, and you are having f3 is 1 kilohertz. So it means for 1 kilohertz, at least your sampling frequency would be 2 kilohertz. But you are undersampling at 1.5, it means it would be aliased. But it is known that it would be aliased, but it would be changed into which frequency, that needs to be determined. And similarly for f4 is equals to 1.5 kilohertz. Again, the respective frequency would be minimum sampling frequency should be at least 3 kilohertz, but we are sampling at 1.5. It means it would also be aliased. It means f3 and f4 lie outside and they will be aliased with what? With your original signal. Okay, so it means here the calculations have been done. So this f3a has been changed into minus 0.5 kilohertz. It means although f3 was what? F3 was how much? F3 was 1 kilohertz, but it has been here. F3 was 1 kilohertz, but it has been aliased component would be as minus 0.5 kilohertz. And the F4 was originally as 1.5 kilohertz here, but it has been now changed into 0 kilohertz. It means your F1, F2, and F3 would be the define your original signal xt, Okay, here we are assuming that your instead of sine wave you're having cosine wave functions. Means the original signal xt, that is actually having the sum of these four frequencies, would appear like this: 4 cos 2 pi f1 t, and this f1 was 0. Means it has been changed. Cos of 0 is 0, cos of 0 is 1, that's why you are having 4. Then here 3 cos 2 pi f2t, f2 was what? F2 was zero point 0.5, then F3 was 1, F4 was 1.5. So it means this x of t signal from where we have started is this one, the given signal. 4 plus 3 cos pi t plus 2 cos 2 pi t plus cos 3 pi t. And it would change into which signal? It would be reconstructed into which signal? It would be xat. And how this xat is determined? The first term would remain as it is because f1 and f1a are same, f2 and f2a are same, but instead of f3, now we are having f3a. F3 was originally 1 kilohertz, but it has been changed into minus zero point 0.5 kilohertz. And then f4 was 1.5 kilohertz, and it has been changed into 0. It means when you put 0 here, your term would be 4 plus 3 cos 4 pi t. The first two terms remains unchanged, but the remaining two terms, that is 2 cos minus pi t and cos 0, would appear. Why they are appearing? Because your f3 has been changed into minus zero point 0.5, and f4 has been changed or aliased as 0. So when you simplify it, what you will get, cos of minus theta would be in cos of theta. It means it would be 2 cos pi t. And again, here we are having 3 cos pi t. The 2 plus 3 would be 5 cos pi t. And similarly, cos of 0 is 1. So it means this 1 would be added with this 4, and you will get as 5 plus 5 cos pi t. So it means this would be your reconstructed signal. Whereas the original signal was what? The original signal was given in the previous page, that is xt was this one, and it has been reconstructed as what? It has been reconstructed as 5 plus 5 cos pi t. Okay, so it means your reconstructed signal would not be same as the applied signal. Okay, so for this take it like this. And now we will just have and spectrum is also shown here. It means an ideal reconstructor is shown through this dotted line. And what you observe here, that for every frequency component, the spectrum would have two things. For example, you are having, for example, cos f1 by 2 pi f1 t. Then you will have two impulses at plus minus f1, and their amplitude would be half. And it is due to the identity that cos theta can be written as e j plus e minus j divided by 2. So it means the amplitude would be reduced to half, and every spike is indicating a single frequency component at its place. What you observe here, that now at 0 hertz, you are having the original frequency signal for 0 hertz, that was having the 4 amplitude, and it would not aliased, but due to f4 original frequency was 1.5 kilohertz, but it has been aliased as 0 hertz. So it means at f is equals to 0, now you are having three components, one due to dc value of this 4, and these two would be generated due to plus minus half. Original amplitude was 1, and it has been reduced to half on both sides. Similarly, you are having the original spikes of original signal of zero point 0.5 kilohertz, and then later this f3 has been aliased also as here, and it has been reduced by its amplitude by 2 by 2. This was the signal f2, and this component of 2 by 2 is due to f3, that was previously lying at 1 kilohertz. It would be aliased, and it is being appeared as minus uh, zero point 0.5 kilohertz. And then due to this thing, we're having two spikes, one at 0 0.5, another at minus zero point 0.5. And the original spectrum, that is the signal before being sampled, it was here at 1 kilohertz, but after reconstructed signal, it has been appeared as 0 0.5 kilohertz. And the last one, that was a 1.5 kilohertz, the original signal was having f4 here, we're having the half of amplitude here, because always when you are having two spikes, one at positive frequency and one at negative frequency, the amplitude reduced to half on both sides. This 1.5 kilohertz has also been analyzed, and this is now being appeared here at f is equals to 0. Okay, so that's all for this problem. I think it has been clear to you. Okay, uh, then we will continue in the next class.